Hi everyone, welcome to this week's live stream from Chem Help ASAP. I hope that you guys are having a good week so far and that you're joining us ready to do some chemistry. All right, so let's get started. Oh, let me move this out of the way. Okay. So last week, there we go, that's a little bit better. Last week we did Lewis structures for various molecules. So I felt like a good tie-in or kind of the next step to do would be to take at least some of those ones that we did last week and use those Lewis structures to predict molecular shape. Now, the theory that I'm going to be using in this live stream is Vsepr, or valence shell electron pair repulsion model. You can see that at the top of the screen right here. It's just easier to say Vsepr, or some people call it the Vsepr model. That's totally fine. It's all the same thing. So there are three main points when using Vsepr. First, it is used to predict molecular shape in 3 dimensions. So you'll have to bear with me on some of the drawings that I will do. I am not the best artist, but I will do my best to represent these molecules in 3D. The other thing about Vsepr is, you can see here, we are going to try to maximize the space between electron pairs. Again, in 3D space, it's very easy to get stuck in 2D when we work on paper or we're working on a screen, but we want to keep in mind that we're working in 3 dimensions. And the other thing we want to keep in mind is that our lone pairs are going to require more space than our bonding pairs. So that's how we come up with these 3D structures for molecules. It's all based on bonds and lone pairs on the central atom. So another thing before I start is we are only going to do shapes that work within the octet rule. So we are not talking about anything that is an expanded octet, and really I'm not even going to do a reduced octet either. We are going to simply stick with our octet rule, or in the case of hydrogen, just having 2 valence electrons. There are more shapes than the one that I'm showing on the screen, but those are expanded octet shapes. Okay, so we have 6 shapes here. They each have a name, but we assign them based on the electron groups that we have, how many atoms are bonded to the central atom, how many non-bonding or lone pairs, non-bonding, lone pairs, same thing. And then we give them a shape. And then the nice thing is this table, and I'm going to carry this table forward to all of our examples, is the computer gave me nice 3D representations of these molecules. Again, I will do my best on screen, but I am not the best artist. The other thing about these pictures is okay, I guess I should start. The central atom is given in this magenta color. The white here, those are atoms that are bonded to the central atom, and the yellow structures are going to be your non-bonding pairs or your lone pairs. Now, before I jump into my first example, let me just make sure that there aren't any questions here. No, it looks like maybe Aaron has a question. Aaron, yes, you can absolutely recommend topics for new streams or for future streams here. That's totally fine. You can also email me at Karin@chemhelpasap.com, and I'm happy to take your request there. And again, if you have a request for a topic, or even if you have a specific problem, let me know, because I will do my best to work in both the topic and the specific problem too. Okay. So let's jump into our first problem here. All right, so those of you who saw last week's live stream will recognize almost all of these structures. And if you didn't see last week's live stream, then they are, of course, under the live stream playlist. And usually the most recent one is up on the page under, recently uploaded. So For our first example, we're going to go for methane or CH4. Now, I am not going to go through all the steps for the Lewis structure because we did that last week. I am just going to draw the Lewis structure. Okay, so carbon is my central atom, and I have 4 hydrogens bonded to this carbon. Again, remember, when I'm writing this here, I'm giving the 2D representation, the Lewis structure. This may or may not match this structure in 3D. So let's first assign this molecule a molecular geometry or a shape. Okay, so again, we've got all of our shapes here. Carbon, of course, is our central atom. I have 1, 2, 3, 4 atoms bonded to carbon, and there are no non-bonding pairs or no lone pairs on carbon. So what I can see is this is not going to be linear because this only has 2 atoms bonded to the central atom. Okay, so this is 3, 2. So what I'm looking for is this 4 here. So you can kind of work your way down the list, or sometimes you can just find it right away. This shape has 4 atoms bonded to the central atom, which is exactly what we have in methane. It has 0 or no non-bonding pairs, so we're on the right track. That means our shape is tetrahedral. I'm just going to go ahead and write tetrahedral underneath here. And this is what our shape looks like in 3D. So you can see the 3D shape here is really not so much like the picture I drew right here. Now, one way that we can represent this 3D shape on 2D paper or a 2D screen is often you will see methane written like this. And you'll see people use what's called a wedge and a dash. So the wedge means that hydrogen is coming out at you out of the paper. And the dash means that that hydrogen is back behind the paper or back behind the screen. And so again, it's trying to represent this 3D structure in a 2D space. Are there any questions about this? Okay, good, Erin. I'm glad that yes, you heard your answer to your question. Okay, so methane, 4 atoms bonded to the central atom, tetrahedral. Here is my best approximation at drawing this structure. Let's go on to our next structure. Okay, so now we've got ammonia. Again, we did ammonia last week, so I'm just going to draw the Lewis structure like we did last week, and then we will assign it a molecular geometry. Okay, so ammonia, nitrogen, as you can see, is the central atom. It has 3 hydrogens bonded to it, and it does have a lone pair or a non-bonding pair. All right, so this, we already can say this is not going to be tetrahedral because we don't have 4 groups bonded to the central atom. So what I've got is I've got 3 atoms bonded to the central atom and 1 lone pair. So I'm looking for that 3-1 combination in the table. So I have a 3 here, but this has 0 non-bonding pair, so that's not it. And if I move down, you can see here are 3 atoms bonded to the central atom and 1 non-bonding pair. That's what I've got. So this shape is trigonal pyramidal. So let's just write that underneath. All right, and the table again gives us a nice computer-generated 3D structure. And you can see again, my Lewis structure and the actual molecular geometry are not matching up that great. So I am going to try and draw this a little closer to this 3D shape. Now remember, this yellow guy up here is the non-bonding pair. I know it can kind of look like an atom, but it's not an atom. So we've got nitrogen, and I'm going to kind of squash these hydrogens down a bit because if you remember the general rules we used for VSEPR, the non-bonding pairs take up more space than the bonding pairs. So what this lone pair or non-bonding pair does while it sits, I mean, the way I've drawn it, it's on top, is it's going to kind of squash those hydrogens down a little closer to each other. And really what you end up doing is you end up creating this triangle-based pyramid, which is why it's called trigonal pyramidal. So you've got a triangle base down here. So again, this is the non-bonding pair just being a bit of a space hog and taking more space than the bonding pair. Any questions on ammonia? Okay, great. No questions on ammonia. Let's go on to the next one. We've got our classic. We've got water. So let's draw our Lewis structure for water. We have oxygen as the central atom. Again, this one was the one that was a little bit of an exception because usually the central atom is written first, but not in the case of water. And that oxygen has two non-bonding pairs, or again, two lone pairs. So what we're looking for is we're looking for two atoms bonded to the central atom and two non-bonding pairs. So we'll go to our table. This one is two atoms bonded to a central atom, but no non-bonding pair, so that's not ours. Here's this one that's two atoms bonded to a central atom, but only one non-bonding pair, so that's also not it. As we keep on going down, here is another two atoms bonded to a central atom, and here finally is our two non-bonding pairs. Okay, so water is going to be this shape. It is going to be bent, and here is the 3D representation. Once again, you can see my Lewis structure. While it is a valid Lewis structure, it's not really representing what's going on in 3D space. I know you have seen water molecules drawn with the bent shape. So I am going to redraw my water molecule. First I will label it as bent. There we go. I'm going to redraw it so it looks more like this bent shape that my table gives me. So the hydrogen atoms come down and we have two non-bonding pairs. Again, remember those non-bonding pairs, those lone pairs take up a lot more space than our bonding pairs. So just like in the case of ammonia, except now we have two non-bonding pairs, it just squashes those hydrogens down and closer to each other, and the non-bonding pairs get more space up. Again, I've kind of drawn them at the top of the molecule, if you want to call it that. So that is why water is bent. And again, you see this just kind of around in a lot of different places, in media, just kind of everywhere. But that is why it's drawn bent. It's because that's what its molecular shape is. Okay, any questions? All right, no questions. Let's go on to our next structure. And this is good because we should be able to go back and do our bond polarities, which is what I want to do. All right, so now we've got another very familiar molecule. We've got carbon dioxide right here. All right, so let's get our Lewis structure. Carbon is a central atom. It is double bonded to two oxygens. And each oxygen has a lone pair. All right, so here is my Lewis structure. Now there are a couple things I want to point out about this one, because usually the first time when students do VSEPR and they're kind of figuring out their Lewis structures, having the non-bonding pairs not on the central atom tends to confuse students the first time they see it. So for VSEPR, all of these non-bonding pairs mean absolutely nothing. You can just ignore them. If they're not on the central atom, then we will not take them into account when we are searching for the correct molecular geometry on the table. So even though we draw them or write them in the Lewis structure, they are not really a part of predicting the molecular geometry. Also, what I want to point out is all of our previous structures, we've only had single bonds between the central atom and another atom. In this case, we have double bonds. But again, you can, for the purpose of predicting molecular geometry, you can just pretend those are single bonds. It does not make a difference. We just want to know how many atoms are bonded to the central atom, but we don't really care if it's a single bond, double bond, or a triple bond. So in this case, in the case of carbon dioxide, for my central atom, I have no non-bonding pairs, and I have 2 atoms bonded to my central atom. So I'm looking for a 2-0 situation. The nice thing is that's just right at the top of my table. So I have 2 atoms bonded to my central atom. Again, it doesn't matter that it's a double bond. I have 0 non-bonding pairs, again, on my central atom. So my shape is linear. And I finally have drawn a Lewis structure that actually mimics what the 3D shape is. So this guy is just linear. I will label it as linear. And I actually don't have to redraw it. I don't know how you would. Maybe you could make it more linear, but this is the shape of carbon dioxide as predicted by Vsepr. So yay, I don't have to redraw this one. Any questions here? All right, looks like we're all good. So let's go on to our next structure. Okay, now we've got carbon tetrachloride, or CCl4. Again, we did do this structure last live stream, so I am going to draw my Lewis structure. Carbon is the central atom, and I have 4 chlorines bonded to that central atom. Now, each chlorine, this might take me a little while, has 3 non-bonding pairs. So if you had a chance to see the last live stream, this structure has a lot of electrons, and you feel like, oh boy, it's going to be a complex structure. But no, it's really not. It just takes forever to draw these non-bonding pairs in. Okay, here is carbon tetrachloride. Again, all of these non-bonding pairs that are on the chlorine, they are not on the central atom, so we do not have to worry about them for predicting molecular geometry. We just want to know about non-bonding pairs on the central atom. But in this case, carbon has 0 non-bonding pairs, and we are bonded to 4 atoms. So I am looking for a 4-0 situation. And if I go to my table, here is my 4-0. And again, that is tetrahedral. So this shape for carbon tetrachloride is exactly like methane. And you might remember methane is CH4, so it kind of makes sense, right? Now I am going to attempt to draw carbon tetrachloride in a 3D shape, again with the wedge and dash. And I think all of my organic colleagues are probably horrified at my drawing skills too, because they are much better at that. So here it is in 3D, and I really should put in all of my lone pairs to be complete. But often, once you're drawing the 3D shape, a lot of times chemists will drop these lone pairs out here. That one was not really very circular. Just because it takes so long to put them in, and sometimes we do get a little bit lazy. Okay, so here is my best rendition at a 3D shape for carbon tetrachloride. Again, the wedge here means that chlorine is coming out of the screen towards you, and the dash means that chlorine is behind the screen or back behind the piece of paper. Okay, carbon tetrachloride. Looks like there are no questions. So let's go on to our next Lewis structure. Okay, now we have sulfur dioxide, or SO2. Again, this was a structure that we did last time, so I'm just going to draw our Lewis structure here. So sulfur is our central atom, And we've got a double bond to one oxygen and a single bond to a second. We have lone pairs on our oxygen and a lone pair on our sulfur. Now, again, if you saw the live stream from last week, you'll know that this structure does have a resonance structure. So in this case, I did choose to put the double bond on the left and the single bond on the right, but those could be flip-flopped. However, in terms of predicting molecular geometry, it does not matter which resonance structure you use as long as you have a valid Lewis structure. All right, so I have two atoms bonded to my central atom, and my central atom has a lone pair. Again, I want to point out that the fact that this is a double bond and this is a single bond really doesn't make a difference. I'm just counting atoms bonded to my central atom. So I am looking for a 2-1 situation. Okay, so this is a 2-0. That's not what I want. Here is my 2-1. This also is bent. So you'll notice in my table, I have a bent shape, which is 2-1, and a bent shape, which is 2-2, which I know seems kind of confusing, but I didn't make up the rules or the table. So we have two structures that are called bent. So let's write this in. So this is also a bent structure, and I will rewrite it so it looks a little bit more like its 3D shape. So just like we've talked about before, I don't like that bond. This lone pair that I put on top of the sulfur shoves those oxygen atoms down and closer to each other. So there's one oxygen, here's my second, and let me put in my lone pairs. At least I don't have as many to draw as I did in carbon tetrachloride. Okay, so here is my sulfur dioxide looking a little more bent. My lone pairs are a little out of control here, but I do have them all there. So that is sulfur dioxide. Any questions about that example? Okay, great. We're on a roll here. Okay, now we're getting into our polyatomic ions, which, yes, also have molecular geometry. So again, we did some polyatomic ions last week in our previous live stream. Remember, when you're dealing with a charged species like a polyatomic ion, you have to take into account the charge. So with the ammonium cation, it has a +1 charge, which means it has one less electron when you're counting electrons. Or you can think that it has lost an electron, whichever way makes more sense to you. So in this case, my nitrogen is in the center, and I have 4. That is not a double bond. I just didn't do a great job drawing that bond. 1, 2, 3. Don't want to forget that 4th hydrogen. So it has 1 hydrogen more than the ammonia molecule. This is the ammonium molecule. So I have to be careful when I'm talking about the names of these molecules that I enunciate very well, because ammonia, ammonium sound very similar, but they're very different molecules. All right, so I have my Lewis structure. Nitrogen is my central atom. 1, 2, 3, 4 atoms bonded to my central atom and no non-bonding pairs. So again, I'm looking for that 4-0 situation. We've seen this a couple times, so you're probably already predicting it, but here we go. 4-0. Again, this is a tetrahedral shape. So just like before, I will use my wedges and my dashes to try and redraw this in a 3D shape. So we have nitrogen. We'll put these 2 hydrogens in the plane, and I'm going to make 1 hydrogen come out and 1 hydrogen go back. I should also be more complete here because this is a charged species. I really need to put it in a bracket and show its charge like this. Now, again, when you get to organic chemistry, often you will see charges that are circled. That's perfectly fine too. It helps that charge stand out more so you can see it. It just kind of depends on your style. We circle charges a little less when we're talking about general chemistry, but in organic, you'll find them circled more often. Either way is totally fine. Oh, and I didn't write down the name for this, so this is tetrahedral. All right, any questions on the ammonium molecule? Nope, we're looking good. All right, let's keep rocking. All right, so we've got nitrate, again, another polyatomic ion. So don't forget, sorry, I circled that 3 too. Since it has a -1 charge, it's going to have 1 extra electron, or again, you can think that it has gained an electron. So the Lewis structure here is nitrogen is the central, and it has 3 oxygens and 1 double pair, one double bond. Sometimes it's hard to draw and speak at the same time. Okay, and that oxygen just has 2 non-bonding pairs. Again, nitrate is a molecule that has multiple resonance structures. It actually has 3 resonance structures because this double bond can either be like I've drawn it on the right, or you could put it going down, or you could put it going to the left. So there are 3 valid Lewis structures, but for our purposes, as long as we have 1, we're fine. Now I am going to remember to put brackets around this and to put the negative charge outside. So we remember this is a charged species. Okay, so for molecular shape, I have 3 atoms bonded to the central atom, and that nitrogen has no non-bonding pair, so I'm looking for the 3-0 situation, which is going to be right here. So this is trigonal planar. Okay, now I guess I want to keep this. Now, I haven't drawn it very well as a triangle there, so I'm going to redraw it, but I'm actually not terribly far off because this is a planar molecule. At least I'm not having to use wedges and dashes. So I am going to draw this. You know, I'm going to switch this oxygen to more go up, so it looks a little bit more like a triangle, or at least it looks a little more like a triangle to me. Okay, almost done with these non-bonding pairs. Okay, and let's get our brackets and let's get our negative charge. All right, so there is nitrate. Again, one thing I want to point out, I chose to put this double bond facing up, but you can put it either on the right or the left. It doesn't make a difference. That is completely fine. So this is the trigonal planar structure of nitrate. Oh, any questions? Okay, good. No, we seem to be good. That's great. All right, one more. And then we'll go back and do bond polarities because we should have time. Yes, good. Okay, so this is sulfate. I don't believe we did this one last week in terms of Lewis structures, but this is another very easy Lewis structures. This is one, again, that has a lot of electrons and you feel like it's going to be very difficult, but it's actually not very difficult. This -2 as a charge, remember, means that you need to add 2 more electrons when you're counting electrons to do your Lewis structure. So this one has sulfur in the middle. It has 4 oxygens bonded to it. And we have lone pairs around all these oxygens. Okay, I'm getting there with these electrons. 1 more oxygen with 3 non-bonding pairs. Okay, and let's put our charge in. All right, great. So here is our Lewis structure for sulfate. Now for molecular geometry, I have no non-bonding pairs on sulfur, and I've got 1, 2, 3, 4 atoms bonded to it. You already know what I'm going for. This is tetrahedral, so I get to use my wedges and dashes again. Okay, so sulfur, 2 oxygens in the plane, 1 oxygen coming out, and 1 oxygen going back. I'm not really a fan of how I drew these oxygens. Let me try again. That's a little bit better. Okay. All of the non-bonding pairs. All of the non-bonding pairs. Okay, last oxygen. Let's get these pairs in. All right, and of course, our brackets. And we have a charge of -2 or 2 minus. Okay, I do want to briefly address one thing. Sometimes you will see sulfate drawn a different way, and it's a completely valid way. So at the beginning of the live stream, I said that I only want to deal with molecules that obey the octet rule, but very often you will see sulfate drawn in a way that does not obey the octet. So I am just going to briefly draw that just so that you can see it and know it. But for this live stream, because I just want to do octet rule, we're going to keep sulfate in this molecular geometry. But sometimes you will see it written with a double bond to oxygens and then a single bond to the other two. So you can see, okay, I haven't put in my non-bonding pairs, but you have 2, 4, 6, 8, 10, 12 electrons around that sulfur. So it is, you could say it breaks the octet. We usually say it is an expanded octet. So sulfur is an atom that can actually take more than 8 electrons. But I don't want to get into all of that. But I do want to show you kind of another common way that sulfate is drawn, just so that you're aware of it at this point. And then depending on how in depth your class goes, some classes only deal with octet and some jump to expanded octet. But again, I just want you to be aware of this. I'm kind of at the very edge of the screen there, of this other version of the sulfate ion. Again, when we go back and hopefully we'll get to do this one with bond polarities, but we're just going to deal with the tetrahedral, which I forgot to label. All right, so that is sulfate. Let's go back to methane, which we started with. Oops, we don't need our rules again. Now let's talk about bond polarities. And this is going to be helpful if you have a periodic table close by. Because what I like to do in terms of comparing electronegativities is I usually just look at how close something is to fluorine. So depending on if you've covered periodic trends or not, electronegativity increases as you move from left to right across the periodic table, and it also increases as you move from the bottom to the top. So everything points to fluorine. Fluorine is your most electronegative atom. Now, a bond is polar if you have a difference in electronegativities. Now, some people talk about if the difference isn't large enough, then it's really not a polar bond. Because we're not going to deal with actual numbers here, we're just drawing arrows. I'm not going to quibble over what the difference in electronegativity is. We're just going to look at, is there a difference, and then is the bond polar? So again, I'm trying to really simplify this down as much as possible. And then as you get better and more comfortable, then you can really start diving into a more detailed and really a more accurate version. But I always like to start with the simple one first. Okay, so as I am looking at methane, what I really want to look at first is, do I have polar bonds? Because if I don't have polar bonds, then I am not going to have a polar molecule. So to determine if a bond is polar, I need a difference in electronegativity between the two atoms. So let's take a look at this carbon-hydrogen bond. Of course, they're all carbon-hydrogen bonds. And is there a difference in electronegativity between carbon and hydrogen? Again, I tend to look at how close it is to fluorine. It's not an exact rule, but it gives you an idea. And yes, of course, there is a difference. So there is a difference in electronegativity. Which one is more electronegative, or which one is closer to fluorine? Well, carbon is. So carbon is more electronegative than hydrogen. So it is going to pull that electron density down closer to it. So let's do green. We'll do a different color here. So I am going to draw an arrow pointing to the more electronegative atom is really what I'm doing. So I'm drawing which way the bond polarity works. So it goes down to the carbon, that is towards the negative or the more electronegative atom. And we usually make the top of the arrow kind of like a little plus sign. So what we've got kind of embedded in here is a plus sign at this end of the arrow and a negative sign at that end of the arrow. So hopefully that makes sense why we draw our arrows the way that we do. So that way we're always drawing the point towards the more electronegative atom. Okay, let me erase this plus and minus and go back to the green. So we do have polar bonds. Now we need to assign bond polarity to all of our bonds and decide if this has an overall dipole moment, or if the entire molecule is polar. So I can draw these arrows in and in and in like this. So I have assigned bond polarity to each of my bonds. Now what I've just realized is I have done this to my 2D structure, and I really need to do this to my 3D structure. So let me just transfer this down to my 3D structure. Okay, so this points in. These are easy. These are in the plane. Now this is going to look a little odd, but remember that wedge means the hydrogen is coming out towards you, and the dash means the hydrogen is behind the plane of the screen or behind the paper. So here are my bond polarities. Now, what I'm really doing here is called vector addition, but if you haven't done physics, that might not make a lot of sense to you. So kind of a simple way that I think about it is, if I am carbon and I am the central atom, and I have 4 friends of equal strength, and they're all pushing on me at, their various angles here. And again, it might be helpful to remember this is a better drawing of the tetrahedral shape in 3 dimensions. So if my 4 friends are pushing on me here, and the friends have equal strength, so I don't have a super strong friend and a bunch of weak friends, will I, as a central atom, move somewhere, or will I stay the same? Tetrahedral can be a little tricky to see at first, but just trust me when I say, as a central atom, 4 friends pushing at you at all of these angles, you do not move. You end up in equilibrium. So they're all pushing at you at the right angle, and you just stay in place. So while this molecule does have polar bonds, overall it is a nonpolar molecule. I know, which can feel a little bit weird. Okay, so we have done methane, which actually I feel like is one of the more difficult ones to visualize in 3D space. Just another tip, if you have a modeling kit and you can hold it in your hands, that can really help you understand just the 3D structure. It's difficult to draw it on the page, and even though it helps that I have these computer generated 3D molecules, there's something about holding it in your hand. So if you have a modeling kit, or you can get a hold or borrow a modeling kit, that can really help with this. Okay, this is methane. I know it was a little hairy. Any questions about that one? Yes, this is definitely a long problem, but we're done. So yay for methane being done. Let's go on to ammonia. Now we've already determined its shape. It's trigonal pyramidal. This time I'm going to draw my bond polarities in my actual 3D structure. So again, remember that ammonia kind of looks like a pyramid with a triangle base. All right, so let's put in our bond polarities. Okay, first, do we have polar bonds? Well, yes, there is a difference in electronegativity between nitrogen and hydrogen. Okay, which one is more electronegative? Nitrogen is more electronegative. So I am going to draw 3 arrows, all pointing to nitrogen. Or you can think of it as they're all pointing to the top of the pyramid. All right, so again, if you want to think of this as vector addition, that's perfectly fine. Or again, I feel like the simpler version is you are the nitrogen, you have 3 friends of equal strength that are pushing on you. Are you going to move? Well, yes, in this case, you're absolutely going to move. You're going to move up, right? So we do have a polar molecule, and its overall dipole moment is in this direction. Now, I do want to mention that drawing this dipole moment pointing up corresponds to the way that I have drawn this ammonia molecule. If you had flipped this 180 degrees, then obviously your arrow would change direction too. So just be aware of that. Okay, so ammonia wasn't quite as bad as methane was, but are there any questions? Okay, good. Okay, let's go to water. All right, again, water is bent, and I'm going to draw my bond polarities in my proper shape. So yes, there is a difference in electronegativity between oxygen and hydrogen, where oxygen is the more electronegative atom. So my arrows are pointing into the oxygen. So again, if I envision myself as a central atom and my friends are pushing on me, am I going to move? Yes, of course you're going to move. And the way that I've drawn this water molecule, you are going to move up the page. So yes, water is a polar molecule, which again, you have probably heard in passing, but this is why water is a polar molecule. How are we doing on time? Oh, good. All right. I thought we were getting a little bit crunched. All right. So that is our good old friend water. Let's go on to carbon dioxide. So, okay, the great thing about this one is the Lewis structure matches the actual shape. So let's just draw in my bond polarity. So between carbon and oxygen, oxygen is more electronegative. So my arrows point out. I'm going to put just one on the top and one on the bottom, although you don't have to. I just feel like it's a little clearer that way. So now again, if you are carbon and you have friends of equal strength pulling out, are you going to move? Well, in this case, no, you are not going to move. Because again, you have friends of equal strength. So this is another example of a molecule with polar bonds, but overall it is nonpolar. Now, when I use the example of carbon dioxide, I like to also show what happens if all right, so I'm going to keep the right-hand side of this molecule the same, carbon double bonded to oxygen. But on the right-hand side, I'm going to swap out that oxygen for a sulfur. It does not change the Lewis structure. Okay, so I still have polar bonds. And I'm still going to point towards the oxygen and towards the sulfur. But these are not equal strength. So the oxygen is much more electronegative than the sulfur. So you can see I've done this on purpose. I drew this arrow a little bit longer than this one. So now instead of having friends of equal strength pulling out at 180 degrees, I still am pulling out at 180 degrees, but I have friends of unequal strength. Basically, I've got a strong friend on the right and a weak friend on the left. So that means that these bond polarities are not adding out. So again, if you think of vector addition, they would add out when we talk about carbon dioxide, but in this case, they are not adding out. And we will have a small, but an overall dipole moment that is there, and it's going to point towards the oxygen. So if you swap out a sulfur for an oxygen, you will form a polar molecule. Now, it won't be polar by much, and some people might quibble over that, but I like to show that it makes a difference if you've got atoms of equal electronegativity on either side or not. Any questions about carbon dioxide? Okay. All right, sounds good. Let's go on to carbon tetrachloride. Now, the nice thing about this is we've gone back to the tetrahedral shape. So at least we've already dealt with that 3D structure. Again, I have drawn it down here with the wedges and the dashes, but keep in mind the actual tetrahedral shape that the computer gave you there in 3D. So yes, I have a difference in electronegativities. I do have polar bonds. In this case, chlorine is more electronegative than carbon. So all of my arrows are going to point towards chlorine. And this one kind of gets smushed a little bit, but there we go. Because I have 4 chlorines around the carbon, again, these are friends of equal strength. So again, that carbon is not going to move. So this is going to be a non-polar molecule. But just like we saw with carbon dioxide, what would happen if we swapped out that chlorine for, say, a fluorine? So I am going to erase this chlorine. And you know what, I think maybe I'll make it yellow just so it's obvious, and put a fluorine in here. So this is a different atom. It's still more electronegative than carbon, but just like before, what we've done is we've added a very strong friend on the left-hand side. So instead of having 4 friends of equal strength, we have 3 friends of equal strength and 1 very strong friend. So again, just like we saw in the previous molecule, you can actually change it so that you have a little bit of a dipole. And in this case, once we've swapped out the fluorine, of course, our dipole is going to go towards the fluorine. It's going to go towards our strong friend. Now, it's not going to be huge, but it is going to be there. So always keep in mind not only the shape, but if you have a symmetrical molecule or not. Again, do you have friends of equal strength either pulling or pushing on you? Okay, any questions about carbon tetrachloride? Okay. I think we can get through a couple more here. All right, so sulfur dioxide. Again, we have already found the shape of this. This is bent, so let's put in our bond polarities. So we've got sulfur and oxygen. Oxygen is more electronegative, so I'm going to draw my arrows down to oxygen, like so. Oh, let me move that out of the way. Again, you can pretty easily see that, yes, if you are sulfur, you are going to move. And in this case, you're going to move this way. So this is a polar molecule. Now, when I do sulfur dioxide, sometimes I also like to do ozone. I'm going to draw that in yellow. So basically, I'm going to switch that central sulfur out for another oxygen. So ozone is O3. And it is the same shape as sulfur. Oh, I drew that sulfur. That's supposed to be an oxygen. Sorry, oxygen. It's the same shape as sulfur dioxide. And so what is tempting is to say, oh, it's bent. there's no way that you can have a nonpolar molecule if it's bent, because your vector addition is not going to add out, or again, if your friends are pulling you, it's not going to be even. But in this case, the thing I want to point out is we have oxygen bonded to itself. There is no difference in electronegativity. So this molecule does not have polar bonds. So therefore, it is nonpolar. So that's sometimes a classic trick that you'll see in problems, is they'll throw ozone in and they want you to kind of do a knee-jerk reaction and say, oh, it's bent, it must be polar. But in this case, no, it's not polar because you don't have any polar bonds. Okay, any questions about sulfur dioxide or ozone? All right, great. We can go on to our next one. So let's go on to ammonium. Again, this is another tetrahedral. So hopefully the tetrahedral are making a little more sense, or maybe at least repetition helps. So between hydrogen and nitrogen, this is very similar to ammonia, except we have an extra hydrogen, which changes our molecular geometry. Okay, so tetrahedral, all of the friends are equal strength, so this is going to be nonpolar. All right, so that one was pretty easy. Let's go to our next shape. Okay, so now we have nitrate, and this is trigonal planar. So again, between oxygen and nitrogen, so this one's a little bit close. If you look at your periodic table, I've got one right here. This is why I keep looking over. Remember, oxygen is closer to fluorine, so it's more electronegative. Oh, whoops, I drew that one the wrong way. Huh. Okay, so here we go. And again, keep in mind the shape, this is trigonal planar. So all of these atoms are 120 degrees from each other. So if you are the nitrogen, again, friends of equal strength, do you move? Well, no, actually you don't move. So another case of polar bonds, but overall a nonpolar molecule. So, of course, my question to you is, how would I make this a polar molecule? And hopefully you'd say, oh, Karin, that is just not a problem. All you need to do is change one of those oxygens into a sulfur. Let's see. Yep. Right? Okay, so sulfur is a weaker friend. Maybe I'll keep this in yellow. So instead of being nonpolar, having everything add out, I'd say you're probably going to go a little bit, well, maybe point it down a little bit more. A little bit this way. So you would be polar, but just by a little bit. Because that sulfur is still pulling, it just doesn't pull quite as strong as oxygen. All right, so that is nitrate. Great, I think we've got time for one more. Let's go ahead and do, well, sulfate is an easy one because it's tetrahedral. So oxygen is more electronegative than sulfur. And because we have a symmetrical molecule, or again, you can think of having four friends of equal strength, this is going to be nonpolar overall. Okay, so those are really going through just about all of our shapes. I think we did do all of our shapes, again, obeying our octet rule. There are other shapes if you go into expanded octet, but in terms of determining polarity or non-polarity, the rules are still the same. You need to determine first bond polarity, and then you need to do vector addition to determine if you have an overall dipole moment. I hope you found this live stream helpful. Thanks so much for tuning in, and let me know what you guys want to see next week. Thank you.